Good afternoon and welcome you all to the 10th day of START 2025. Today's first lecture and 18th lecture of this series is on Advanced Propulsion System for Future Space Exploration by Sri Hattan, Associate Director, Liquid Propulsion System Center, ISRO, Tirunelveli. We have with us Sri Nihal K. to moderate this session. I would like to introduce the moderator. Sri Nihal K. took his BTech degree in aerospace from IIST in 2019. Currently, he is working as scientist in Human Space Flight Group in the liquid propulsion area of LPSC. He is involved in activities related to Gaganyaan, orbital module propulsion system, and environmental control and life support systems. Over to Mr. Nihal to introduce the speaker and to moderate the session.
Thank you, sir, for the brief introduction. Good evening, all. So today I have been honored to introduce our speaker, Sri R. Hattan. So Sri R. Hattan, a mechanical engineer, was graduated from TKM Engineering College, Kollam, Kerala in the year 1988 and joined in VSSC ISRO in Polar Satellite Launch Vehicle Project in the year 1990. Considering his contribution to the PSLV program, he was designated as Deputy Project Director, further as Associate Project Director, and later as Project Director PSLV in the year 2017. He was the Associate Vehicle Director for 13 PSLV missions, including the prestigious PSLV C-25 Mangalyaan Mars Orbiter mission, Vehicle Director for another 11 PSLV missions, including PSLV C-37, which lofted successfully 104 satellites in a single go, and finally the Mission Director for 6 PSLV missions from PSLV C-39 till PSLV C-44. Sri R. Hattan is also recipient of Team Excellence Award and ISRO Merit Award, considering his significant contributions towards PSLV program, and ASI Award for contributions in rocket and related technology. Subsequent to his stint at PSLV, Sri R. Hattan later designated as the Project Director of ISRO's most ambitious project, Gaganyaan mission, under the Human Space Flight Center of ISRO. Currently, Sri R. Hattan is the Associate Director of LPSC. With this brief introduction, I will now hand over to Sri R. Hattan.
Thank you, Mr. Nihal. Hope I am audible to all of you. So, first and foremost, welcome to all of you and very good afternoon. Actually, this subject, this Advanced Propulsion Systems for Future Space Exploration, this is tailored to you with cutting-edge knowledge in one of the most crucial areas of modern space exploration. Basically, as you know, that this understanding about our propulsion technologies, it is very important as we continue to push the boundaries of what is possible in space. From satellites to deep space mission to Mars and beyond, the propulsion system is playing a very, very key role in determining the success as well as the sustainability of the endeavors. And though it's on advanced propulsion system, what I thought is, we will just cover traditional chemical propulsion system and to the next generation systems, like we talk about these ion thrusters, we also will talk about this nuclear propulsion and so on. So first, let us get started. Hope all the slides are also visible to you. As you know, in ISRO, basically there are various generations of launch vehicles which have already been designed as well as developed, realized, tested, and then flown. So what is shown in this figure is a series of such launch vehicles, starting from the sounding rockets at the extreme left. These are all very small rockets, which get into the atmosphere and with a small payload. And the main purpose of these payloads are just carrying out some measurements of our atmosphere. So these, even today also, the Rohini is a kind of a sounding rockets. It's called RH, RH300, RH500, 560, like that. Different classes are there. Even today also, these are also being launched, mainly for carrying out such purposes of carrying out the measurement of the atmosphere. And moving further towards the right, you are seeing two small launch vehicles, which are called the Satellite Launch Vehicle 3, SLV, and similarly the ASLV, Augmented Satellite Launch Vehicle. These two were the initial generation of the launch vehicles during the 1970s and the 80s. And the project director of the satellite launch vehicle was none other than our former and late President Dr. APJ Abdul Kalam. And there were a number of missions of both SLVs and ASLVs. Of course, initial mission was a failure, but then later missions of SLVs and ASLVs were grand successful. But then when we graduated the rocket technology, we moved on to the next generation launcher called the PSLV. This has come from the 1990s. And even today, the PSLV, the Polar Satellite Launch Vehicle, is one of the very workhorse launcher of ISRO. And recently, on 30th of December last year, we had a grand successful mission, which has taken SpaceX. A few days back, we had the space docking experiment. The two satellites, SpaceX A and SpaceX B, was launched by the PSLV, and then we had a mating, or we had a docking of these two satellites, which got demonstrated a few days back in the orbit. So then India became the fourth country after the US, China, and Russia to have this technology of docking in space. And then moving further right, we have the GSLV, Geosynchronous Launch Vehicle. This also has come into operation from 2000s onwards. This is a launcher which is actually designed for launching geosynchronous satellite into a geostationary orbit. And moving further right, we have the LVM-3. That is called the Launch Vehicle Mark III, which is otherwise a nickname called the Fat Boy. Because out of the group, this is fat in size, so it's a name like that. But otherwise, it is a Launch Vehicle Mark III, which also is intended to carry geostationary orbits, geostationary satellites into geostationary orbits. And to just note that, this particular launcher, already 7 missions we had, and all the missions were a grand successful one. Even the latest, the Chandrayaan-3 mission was executed grand successfully by this particular launcher. And in fact, you also please note that this launcher is designed for carrying humans into the orbit. That is, as part of human space exploration, this launcher is also getting human rated. And that mission also we are going to have in the first half of this year with the unmanned missions. And the far extreme right is a small launch vehicle. Again, you are seeing, this is named as SSLV, which is actually the small satellite launch vehicle. This is also looking into the market of carrying small kinds of payloads of the order of 500 kg into a 500 kilometer orbit. This launcher has been optimally designed with a low cost and anytime launch, so that once the demand is there, within a week, you can realize and then integrate and test and then launch. So that is how the small satellite launch vehicle. So these 4 launch vehicles, the PSLV, GSLV, Launch Vehicle Mark III, as well as the SSLV, are today currently in operation. Why I have put this slide is only to tell you that these gigantic vehicles, which are 40 meters or above tall, and which are weighing from 200 tons to almost 600 tons, they are all using propulsion systems of different kinds, like solid propulsion, liquid propulsion, and that even we call it as storable as well as cryogenics. Maybe we will go into the details of that later. Just to put you in perspective, all these things are powered with the huge propulsion systems. Now let us see the satellite propulsion. Similar to the launch vehicle, we have various satellites, starting from Aryabhatta. In the year 1975, we have launched, and then various kinds of the Stretch Rohini satellite series, which is otherwise called STRAS. And today we are talking about very heavy launches such as GSAT, Geosynchronous, the Satellite 11 and Chandrayaan-3. These satellites also carry the most important, the propulsion system, because once you are reaching the orbit, you need to maintain the orbit. That is the 3-axis control in pitch, yaw, and roll that is maintained by the propulsion systems. And we also use bipropellant or even monopropellant liquid propulsion thrusters to do that. So, and then we are also seeing the bottom, whatever that is shown is the application, what for the satellites are put in orbit, like Earth observation, SATCOM application, that is satellite communication, navigation application, it's called NAVIC, then disaster warning like cyclones, and tsunami, kind of a disasters, if it can be one. And then there are various strategic applications to, monitor the borders and things like that. So various applications, various kinds of satellites are provided, and various kinds of propulsion systems are also there to ensure that the satellites remain in the orbit with its 3-axis stabilized. Now let us look at what are the classification of propulsion. As you are all students and there are space enthusiasts, some of you might be knowing that there are various kinds of propulsion devices. Basically, propulsion devices are the one which keeps you moving forward. So we can have like a stored gas propulsion. The extreme left top, it is put as stored gas. And similarly, we have a propulsion system called chemical propulsion system. Under that, we have different classifications. So that is where we were telling about the solid propulsion using solid kind of a fuel, liquid propulsion using a liquid propellants, and then we have the hybrid, means both solid and liquid put together. And similarly, under the liquid propulsion, we have two categories. One is by pressure fed. A simple meaning is that the propellants are fed from the tank to the engine by pressurization. And there is another type called pump fed, where the propellants are fed to the engine by pumping method, by taking the propellants from the tank and building up a high pressure, because you need a higher flow rate and a higher thrust. So you need a higher pressure. We go for a pump fed. Moving on to the right, we have the advanced systems. We talk about the electric propulsion. There again, the different versions are there. It is called electric thermal propulsion, electromagnetic propulsions are there, electrostatic propulsion devices are there. We will see it later. And similarly, we have an advanced system, advanced propulsion called the nuclear propulsion. There again, nuclear thermal propulsion is there, nuclear electric propulsions are there. And then we have further propellantless propulsion. That is where the propellants are not required using the solar power or within the, the sun pressures, the photons. Using that, we can sail in the orbit, and we have a laser propulsion. So these things, some of these, we will see it in the later. Now, we will address each one of them in very quick session, like stored gas propulsion. As the name indicates, the gas is stored in a gas bottle. That you see, the yellow colored, the gas bottle at the top. It is called propellant tank. This gas can be helium, this gas can be nitrogen or whatever it is. And that is at a high pressure. And then we have a series of certain valves and the regulators, so that once you open these valves, the regulators will regulate it to a needed pressure. It could be 18 kc or it could be 20 kc, depending upon what is the thrust that you want. And that is a simple, very simple mechanism. Like, you fill a balloon and you just open the balloon, the gas comes out, the balloon moves forward, something like that. So here again, the gas is stored in the gas bottle, and then it is fed through the thruster by the operation of various valves and through the operation of regulators. So these are all mainly used for control systems in satellites, when your demand for the thrust level are very less, of the order of 1 Newton, 10 Newton kind of a thing. So these are all mainly for that. Now, when we look at the solid propulsion, these propulsion motors, they are all ranging from small motors to big motors, which are all finds its application in the launcher or in the launch vehicle application. As you see here, the cross-section of that is a very simple system and very robust also, very reliable, because the number of elements are less. So you see that there is a yellow portion, which is called the combustion space. There is a gray portion, which is actually the propellant. So, and then there is a motor case. So and you are seeing a red colored badge, which is on the left side. This is the igniter. So for igniting a solid propellant, you need an igniter. So igniter is ignited by means of electrical command. So you give a command from the onboard, and using the battery, you supply the electrical supply to the skip, a small electrical wire, which will raise the temperature, and that will ignite this very small solid propellant inside the igniter. So once the igniter catches, immediately it ignites the main propellant, the gray color, the full length of the chamber, it gets ignited. And once the total propellant gets ignited in a controlled way, combustion will happen, and then it will exhaust to the right side. That is called the nozzle. It is basically a convergent divergent. It is called a D-level nozzle. Who are studying the space, they may understand what is the D-level nozzle, which is again a conversion divergent nozzle, where the high pressure is getting converted into high velocities of the order of, in terms of Mach number, it will be very high. When we are having a Mach number of 1 at the throat, which is called the sonic velocities, and they said you will have a very high Mach number equivalent to the velocities of something like 2000 meters per second or even much higher. When we talk about solid propulsion, it must be 2000 or 3000 meters. But when we talk about advanced propulsion systems, it can be as high as 10,000 meters per second. Or you can always convert it into a Mach number, because Mach number, one Mach number is something like 340 meters per second, the velocity of sound. So always you can convert that. So here you get a huge power, a huge thrust, and which is what is required for a launch vehicle when you take off from the earth to overcome the gravity. So naturally, all the launch vehicles will use these kinds of boosters, like a solid boosters. Moving further, we have another propulsion called liquid. Here, the main advantage is, compared to solid, this liquid, you have a better controllability. And you are also having a higher performance in terms of efficiency. And in the rocketry, when we call it as efficiency, we term it as in the terms of specific impulse. Especially it is called ISP. That is the amount of thrust that you get when you fire 1 kg per second of a propellant. So this is a parameter which otherwise, in nominal automobiles, we call it as horsepower. So here the horsepowers are in millions. So we don't normally talk about the performance in horsepower because it's in lakhs and millions. So, but then we derive a parameter called ISP. So the liquid propulsion system have got a better ISP or a better specific impulse. That's why we say it's a higher performance. Better controllability, because always you can shut off or switch on by just switching on the valves or closing the valves or opening the valves is always possible. And another advantage is basically, you can always flight test this, because in the ground you can test it and use it for the flight. Whereas solid propulsion, it is a one-time operation device. Whatever that solid propellant is stored, once it is ignited, the full propellant will be going out. So there you can't test it. So here in the liquid, we have a restart capability. You can switch off and switch on. All these things are there. So that's why liquid propulsion is gaining advantage over solid propulsion. But then solid propulsion has got its own advantage of creating a high power, high thrust. Very short time, you can create a high thrust. And for as a boosters, always people use solid propulsion. Even in our Indian launch vehicles also, all of the launch vehicles, whatever we have seen, PSLV, GSLV, LVM3, or in SSLV, you are seeing a solid boosters giving the initial needed thrust to overcome the gravity and things like that. Of course, any propulsion has got its own disadvantages. In terms of liquid propulsion, it has got a number of parts, therefore it is more complex. And the reliability also, maybe the reliability always you can build up by going for a number of testing. But it always has more preparation. You need to fill the propellant at the launch pad, being a liquid like that. So these are all the things with respect to the liquid propulsion. And it's a simple sketch which is shown here, that you have a rocket, you have two tanks. Always for a combustion, you need three things. One is the oxidizer, other one is the fuel, and the third one is the temperature. These three things form the three vertex of a triangle. That is called the safety triangle, or it's a fire triangle. So here we have fuel, here we have an oxidizer. So where from the temperature comes? It can come either from an igniter, or when the propellants mix, that is called hypercooling. That means certain propellants are the fuel and oxidizer. When they mix, they create a huge exothermic reaction. And this reaction, it produces huge amount of energy, thermal energy, which ignites the propellant. These are called hypergolic. But then there are certain propellants which are not hypergolic. For those propellants, we need an igniter, like a cryogenic propellant. So we have a different categories called monopropellant, bipropellant, and bipropellant also. We have a pump fed and pressure fed, which we will see it. So here, basically, as you see in the picture, both the propellants will flow through valves to the engine where it mixes, and when it gets ignited, high pressures are created, and these high pressures are getting converted into high velocities in the nozzle, what is seen on the right side, extreme right, like a convergent divergent, where the exhaust is going at a very high velocities. So basically the thrust you are getting because of the Newton's third law, every action there is an equivalent opposite reaction. So here the mass as well as the exit velocity, it is called m dot into velocity, exit velocity. That is the momentum which is actually pushing the vehicle forward. So you get a reaction back which is acting as a thrust. That is how any propulsion will work on. Now you see the monopropellant. As the name indicates, it is a single propellant. There is only one propellant, which is actually simple. It is very simple. You just store it in a tank, you open the valves, and then it goes to the thruster. Then what happens is this monopropellant, it is admitted through a catalyst, and the catalyst bed, it is maintained at a certain temperature, maybe to 300 degrees centigrade, where the propellant, something like a hydrazine, it is a propellant. Or even hydrogen peroxide is another propellant. These gets dissociated or decomposed, creating high temperature and pressure, and that is admitted to the nozzle to get the required thrust. So these are all, it is used for control purposes in the satellites, and then in all our IIRS class of satellites, these kinds of monopropulsion systems are employed. Now let us see what are the various, the propellant combinations in a bipropellant. As the name suggests, there are two propellants, fuel and oxidizer. These are the propellants. Of course, there are various kinds are there. These are all only examples. You see the storable propellant. The meaning is it can be stored in the earth conditions. No separate environment is required to store the propellant in the earth-like environment, like in an ambient pressure and ambient temperature. So the propellants oxidizer like nitrogen tetroxide. Fuel is put in red color everywhere. The red colors are fuel, and there's an unsymmetrical dimethyl hydrazine. This is one combination, or you are having another combination, nitrogen tetroxide with monomethyl hydrazine. These are all storable. You need not have to have a different kinds of environment to store it in the tank cages. Whereas when you come to cryogenic propellants, these are all, as the name suggests, it is cryogenics. Means it is below minus 150 degrees centigrade. You can imagine the water becomes ice at 0 degrees centigrade. We are talking about 150 degrees centigrade below that. So minus 150 below that, anything is cryogenic. So the oxygen and the hydrogen, or even the nitrogen for that matter, all these are in gases, and below these temperatures it will become liquid. Liquid hydrogen will become liquid only when you go to 20 Kelvin or even minus 253 degree centigrade. And similarly, liquid oxygen is also, the gaseous oxygen becomes liquid at 90 Kelvin, minus 183 degrees centigrade. So such kind of low temperatures we are dealing is called cryogenic. Similarly, we have a semi-cryogenic where one propellant is H-storable, other propellant is cryogen. Here the cryogen is liquid oxygen, which is again 90 Kelvin, and kerosene is a room temperature, maybe 300 Kelvin you can store kerosene. But then it is a high quality kerosene, it is not the kerosene we use in a house. It is a superior kerosene, or something like an aviation turbine fuel, or we call it as an ISRO-zine. ISRO kerosene is called ISRO-zine, something like that. And similarly, already we dealt with monopropellant. This could be hydrazine, hydrogen peroxide. So these are all the various kinds of the propellants that we employ. Now let us look at, yes, this particular thing also, this we have already seen, the rocket where the tanks are put. On the right side, there is a picture showing the nozzle as well as the fuel and oxidizer tanks. And once you open the valves, it gets. And then here, only one point I would like to tell you. Whenever we deal with the liquid propellants, fuel and oxidizer, they are stored in liquid form in two different tanks. And therefore, the ratio at which you are admitting the oxidizer and the fuel to the engine is very, very important. We call it as a mixer ratio. And then the mixer ratio is nothing but it is a ratio of oxidizer to the fuel. That is what is put in the equation in the bottom. Otherwise, it is conventional things. And then cryogenic propellants always need an igniter, whereas H-storable, hypergolic, we defined earlier, hypergolic are the one where when fuel and oxidizer mixes, exothermic reaction is generated, high amount of heat is generated, and that ignites the propellant. That is where it's called hypergolic, whereas cryo is actually you need an igniter. So moving further, you can see again a pressure fed and a pump fed here. The pressure fed, as it is shown in the left side, you can see two tanks, simply the propellants are filled, and there is a space where you fill the gases. It is called allayed space, which is not filled with propellant. And in this allayed space, we pressurize either with nitrogen or helium. It simply pushes the propellant. Like, you keep water tank in our house at the over tank, you simply open the tap, the water flows to the pipe, something like that. Here, these propellants are stored in a tank. It is pressurized by means of a pressurization bottle, which is shown as a spherical bottle in the top. And once you open the valves in the below, about the nozzle, the propellant simply flows, and there it meets and combustion takes place. You get a combustion, you get a thrust. It's called the pressure fed. On the right side, whenever you want higher flow rate, higher thrust, you go for a pump fed because you need a higher pressure. One way is you pressurize the tank, but then when you pressurize the tank, you have to build a big thickness for the tank material, and that will lead to very high inert mass. So we always do this calculation of thrust weight, and then which is better, whether pressure fed or pump fed. Then we find pressure fed, pump fed is better when we go for certain, higher thrust kind of a thing. Where we use all the pumps, you see below the propellant tank there are pumps. These pumps will take the propellant from the tank and then it will pump it to the engine or to the the thrust chamber. And then, but then for driving the pump, you need a turbine. So we use a gas turbine. So this gas turbine also has to be driven by gas, hot gas. So how do you produce the gas? So the same propellant which is coming from the tank to the nozzle, whatever that is going outside the pumps, especially we call it downstream of the pump, a small tapping is taken. You can see there is a small tapping is taken both in the fuel line and in the oxidizer line, and then it is given to a gas generator where the gas is produced, and that gas runs to the turbine. Maybe the arrow mark or the mouse can show that. So that goes to the turbine, and then the turbine is run, and these gases will be dumped on board. It will go out. So some energy is used for driving the turbine, and this turbine will drive all the pumps, and the pumps will take propellant from the tank and pump it to the engine. That is how the high flow rates are getting produced and high thrust is being produced. This is a simple operating principle of a pump fed system. Now you see, even in a pump fed system, there are different thermodynamic cycles. How the combustion cycles are taking place. We have a gas generator cycle, we have a stage combustion cycle, we have an expander cycle. There are different kinds of cycles are there, depending upon the maturity of the design, depending upon the expertise in the design. So we adopt certain design cycles. Here you can see the gas generator cycle. This is what we have explained in the previous slide, where a portion of the propellant will be taken from the pump downstream, that will be admitted to the gas generator. Gas generator, the combustion will take place, that hot gas will go to the turbine will be run, and the gas will come out like an exhaust. And once the turbine is run, this turbine will be driving all the 3 pumps. Maybe if you want different speeds, we put a gearbox there. For the oxidizer, if you want a different speed, we turn the gear according to the gear ratio, the speed will be changed. So this is called the gas generator cycle. Here, one point to be noted is after running the turbine, the gas, which is again contain the energy, it is simply dumped on board. So here you're not getting a full efficiency there. Now, compared to the right side, there's a closed cycle. Other one is an open cycle because the gas is going out after the gas generator. Now you see on the right side, here again, the principles are a small difference is there. You can see, you can trace the oxidizer, which is a blue line. From the pump outlet it comes, and then there is a tapping there. A small flow will go to the pre-burner, or the pre-burner is otherwise it is a gas generator. Similarly, you can also trace the fuel line, which is red line. From the pump it comes, entire thing is going through the chamber. You can see it is cooling the chamber, and when it's getting cooled, the propellant will get heated up, and that it will, the temperature is going up. More pressures are created, that is admitted. The entire propellant goes to the pre-burner, and a small amount of oxidizer is coming, that it will mix, and then you are getting, that high temperature, that will drive the turbine, and then the turbine, again, the whole gases will come back to the main chamber. So that means here I am not losing the gases, I am taking it back to the thrust chamber, and I am getting a good efficiency. So this is called a stable combustion cycle. You can move further. So now hydrogen, cryogenics, already we have defined, always the cryogen has got a very high, the power, the thermal power is available. There is a good advantage over there. All these things are the only disadvantage is this is very lightweight, and therefore you need a bigger tank volume to accommodate this much huge quantity of hydrogen. Otherwise, enthalpy wise, it is having a very enthalpy. Always people go for cryo because of higher enthalpy, but you cannot use it as a booster stage because huge tanks are required to store the propellants. So it has got an advantage and disadvantage. So according to the requirement, either we will use it in the booster stage or we will use it in the upper stage of the rockets. Yeah. Now this is the same thing. I think this we can skip. Already we have told this. These are all the various, the cryo engines. USA, ESA, China, Russians, and India. You can see all these engines are used in the upper stage of the respective launchers. And you can see the right bottom, we have 2 Indian engines, which is called CUS. There is a cryo upper stage, and similarly it's called C20, where the cryogenic engine with a 20-ton thrust level. So this thrust you can see 73 kilonewton as well as 200 kilonewton. It is comparable with the other USA or China or the Russian launchers, wherever they use the upper stage. So similar engines, we have totally indigenized. The CUS is fully indigenized, and the C20 is an end-to-end indigenized engine. So India can be proud of that. The total cryogenic technology we are having to build even bigger cryogenic engines for the future launch vehicles. Now, semi-cryo, as the name suggests, one part is storable, other part is cryogen, that is a liquid oxygen, and of course kerosene. So naturally, when we go for semi-cryo, one important parameter to be noted is the density impulse. Density multiplied by the specific impulse. This plays a very important role for selecting any propulsion when we design the full launcher. So normally the semi-cryogenic engine or the semi-cryogenic propulsion we use for a booster stage. So here I have 2 advantages. One is it has got a good density, second, so that your container size can be less. Other thing, it has got a moderately high ISP compared to the edge storable. Already we have seen it is about 330 to 350 seconds. So that way the density multiplied with specific impulse, it gives a good number. Probably in one table I will show you. Maybe the next, maybe we will see that. You can go to the next where we can see the table here. In the table you can see the last row. It is called the density into ISP. It's called the density impulse. You can see semi-cryo something like 3000 plus, whereas storable is only 2800 and cryogenic is about 1500. So for all the booster stages, we use semi-cryogen. Semi-cryogen is also one technology which India now is almost done. We had certain engine tests. Now we are going to full steam. Maybe in a year, the semi-cryogenic stage also will come. So our plan is the bottommost line you can read, the GSW Mark III, we are planning to convert the core stage. Earlier we have seen it's a storable stage, which we are planning to convert into a semi-cryogenic stage so that we can increase the payload capability by about 700 kg. So that is where the booster stage we will use. But if you use for the upper stage, that is what is shown in the above line. In the current LVM3, the upper stage is cryo. If you are replacing with the semi-cryo, there could be a payload loss because there the performance matters in the upper stage. So that's why there is a payload loss. But normally when you go for the booster, always there is a payload gain. Now let us see the hybrid motors. As the name suggests, hybrid motors are the one which use both fuel and oxidizer, where fuel is the solid and the oxidizer is liquid. Here the advantage is you can always start and stop. Unlike solid, if it is a fully solid, once you start, the total motor will burn till the total propellant is exhausted. Whereas a solid plus liquid means once I switch off the oxidizer, the combustion can be stopped. So it has got that advantage. It has got a moderately high the specific impulse also. Here the oxidizer what we use is either it can be a liquid oxygen or it could be a hydrogen peroxide or nitrous oxide. So it has got a shutdown and the restart capability is always there. Depending upon the mission, we select these kinds of things. Anyway, currently in none of our launch vehicles we are using hybrid, but already this particular engine has been developed and it has been test proven in our ground test facilities. Yeah. So this again, this table I think we have already dealt with, where I wanted to only tell about the ISP. Solid we are getting around, last column we can see around 290 maximum, at storable we get up to 315, semi-cryogenics up to 350, whereas the cryogen we can get even up to 440 to 460. So this is the kind of the efficiency that we get depending upon the different kinds of propulsion. So it is all left to the designer and his expertise available to select what kind of propulsion he is expert in, and then accordingly the launcher can be designed. Yeah. Yes, these three launch vehicles also we have seen. Maybe we can see further. And these are all the liquid stages. Like, the extreme left, we can see the PSLV. It is using two liquid stages, which is again using the H storable, like, nitrogen tetroxide and hydrazine. And similarly in the middle, GSLV Mark II, we are seeing there again the second stage and the cryo stage. We are seeing that. And the right side, we have the LVM3. Why this slide is put is just note that launch vehicle Mark III, we have two major booster stages are there. One is the L110. Always the number represents the propellant loading. 100 tons of propellant. Similarly, C25 is there with 25 tons of cryogenic propellants. Just remember these two stages, L110 and C25. I'll be referring this in my next slide. In my next slide, you can see on the left side, there is an LVM3. You can see the bottom, the middle colored one, you can see that is the L110 stage today. This particular stage, we are going to replace with a semi-cryogenic stage. You can see SC120. 120 refers to 120 tons of semi-cryogenic, which consists of liquid oxygen and nitrogen. So once that L110 stage is replaced with semi-cryogenic, we get a good payload advantage. Added to that, the top stage, the cryogenic stage, which is currently C25. 25 tons only, we are using the propellants, which we are having a plan to upgrade it to C32 with 32 tons propellant loading. And added to that, even the engine thrust also, we are planning to upgrade it from the current 20 ton to 22 ton. So by doing both these changes, you can see the bottom, the payload capability is enhanced by more than 1 ton. From 4 ton to 5 ton or even 5.1 ton capability. This anyway we are going to demonstrate in a matter of another 1 year. And on the right side, we are going to have a new gen launch vehicle. It's called next generation launch vehicle, which is really required for us when we are talking about going to moon and all, in the future. This is very important, which the designs are already in the final stage and the realization actions are also taken. You can see there is a core stage which is called the LM450. It is a LOX methane. This again, make a note that it is using LOX and methane. Again, both are like, cryo. LOX and methane, which is again low cost because the methane is again cheaper. And then it is about 450 tons of propellants are used in the core stage. And we have a second stage with LM120 and we have an upper stage with C32. This particular launcher is gigantic. It is something like 5 to 5.4 meter in diameter. And then height is about 90 meter tall, which has got a huge capability of taking 20 to 30 ton to the low Earth orbit, or even to up to 10 to 12 ton to the geotransfer orbit. So this is a huge launcher in a matter of few years. This launcher also will come, which is actually a dream for us for taking humans to moon in the future, when our vision is already there to put our man on moon by 2040. So for that, this launcher also will be coming into picture. You can see the kind of engines on the right side where we are clustering all the engines together for the core stage. And for the second stage, LM120, we use 2 of them for our second stage. And upper stage, of course, it's a cryo. So moving further, now again, this is already we have dealt with. Maybe we can move further. Now let us talk something about our advances. Green propulsion. Green propulsion, basically, all these propellants we talked about that's storable, they are all highly toxic. So when we talk about they are not eco-friendly. So when we talk about that, we need to think of which kind of propulsion can give me a better eco-friendly propellant, environmental friendly. When we think about that, there are propellants like, hydroxyl ammonium nitride or even ADN, kind of ammonium dinitride, like of propellants are there, which is otherwise called green propulsion. That means once these decomposes, you get, the exhaust will be totally eco-friendly, something like steam or carbon dioxide or carbon like that only is there. So these kinds of green propellants are also, we are doing R&D, as well as even now, many thrusters have been designed and tested. Maybe in the future, we will be using these kinds of propulsion system for our satellite application. In fact, the greenness of the propellants are measured by means of lethal dose and lethal concentration. That way, that is called LD50 as well as LC50 kind of a thing, where, when we expose these kinds of propellants, 50% of the population should not get affected. So when we tell that quantity of the propellant required, when number is higher, means it is more greener. For extraordinary or chemical propulsion, the number will be on the lower side. That is how the rating of the greenness is done. So these are all some of the green propellants, like, HAN, ADN, or even a bipropellant green propellant is there, something like hydrogen peroxide and ethanol, or hydrogen peroxide and isoleucine. So these are all already we have tested, and maybe soon this may find applications in our satellite. Now, again, it is only to show you that this green propulsion we have used even in the human space mission by Americans in the first, the Mercury, which has carried Alan Shepard as well as John Glenn, the astronauts from the America. They have all traveled in Mercury, and that uses these kinds of green propulsion for controlling the modules in orbit. Similarly, the Soyuz, which is there in the bottom, which is a very, very versatile space capsule designed during the 1950s, and even today, so many flights have taken place, which is also using monopropellant for their, the on-orbit control, or even during the descent control. Mainly, they are using for the descent control. Yeah. Now let us see the advance again, the nuclear propulsion. Here, nuclear thermal is there. As the name suggests, basically, it is very simple. You have a nuclear energy, nuclear fuel, something like uranium, U-235, or even U-233, kind of a nuclear systems are there, which, you can always use that nuclear fission or a fusion to generate huge quantity of heat, and that heat will be, it will be used for raising the temperatures or converting the low pressure to high pressure of the propellants like hydrogen and all. And this high pressure, the gases will be pushed through a nozzle so that you get a thrust. So that is what it is called, the nuclear thermal propulsion. So here, basically, huge quantity of heat is generated because of the nuclear fission and fusion. So you get a huge thermal power. That way, you get a higher ISP. So here, when you get a nuclear thermal propulsion, maybe NTP, like what is shown in the bottom side, the red color shows the hydrogen, the nuclear reactor, and there is a hydrogen tank on the right side, blue color. Hydrogen is admitted to the nuclear reactor, where a huge amount of heat is generated because of the nuclear fission of the fuel, and that heat is used for pressurizing or increase the temperature and pressure of hydrogen, which is ejected through the nozzle by a thrust. So you get a higher thrust, and a huge amount of energy is there. So good specific impulse you get, and in a short time you can reach the destination. So it has got that kind of an advantage. So like moving further, you can see the various engines which have been designed by Americans and Japanese. So the Kiwi is again Project Rover. It is like Kiwi is like, flightless bird. Like that, this has already been tested. It has never flown. This is called Project Rover during the 1959 and 60. And similarly, the nuclear energy vehicle for the launch vehicle, especially for the rocket vehicle assembly. So this propulsion called the Narva, which is again, it has not taken off, but then this testing also have taken place during the 1970s, and this also by the Americans. And on the right side, we have the Russian. This also uses liquid hydrogen, and then there is a nuclear reactor which is used for generating the thermal power to convert this liquid hydrogen into gaseous hydrogen to a very high pressure and pushing it through the nozzle. These are the kind of thrust that you are getting. For the Russians, you are finding around 35 tons or 355 kilonewton, and the American engines are also giving you almost 24 to 25 tons of propellant. So these are all the kinds of the nuclear thermal propulsion engines, and we can see the latest ones are the Draco as well as the Copernicus, again by the American companies. They are again working on the nuclear propulsion, and even you might have heard about the Prometheus, the project which has been taken up, and today it is all shelved. There is also planned to work by nuclear thermal propulsion or nuclear electric propulsion. So the principles are same. Using the nuclear fission, generate the heat. That heat is used for heating the propellant, hydrogen, and then the propellant is getting converted into gas to a high pressure, high temperature, pump it to the nozzle, get the thrust. In the nuclear electric propulsion, what we use is these kinds of same thermal energy is produced, and this thermal energy is converted into electrical energy. Probably a gas will be heated, that gas will be running the turbine will run the generator, and then electricity will be produced. This electricity is used for static, the electric propulsion devices. So that is called the NEP, or the nuclear electric propulsion. So this is the other kind, which I have already explained. So here again, the bottom one you can see, Project Prometheus. So this is anyway, it is shelled, but then this gives very high ISP. This particular electric propulsion, something like 3,000 to 4,000 seconds also it can give. So here again, the work already, we are also doing some work towards that. Maybe it all will come in due course of time. This is again forming part of advanced propulsion. Now coming to the electric propulsion, there are three categories: electric thermal, electric static, electromagnetic. The three things are now basically, you can see the electrothermal, basically as I said, using the electrical energy. You may ask me where from the electric energy? It is from the battery or from the solar panel of the satellite. Use the electric energy to to heat the propellants and then eject it through the nozzle. So it's an electrothermal. And then electrostatic is nothing. That is, you have a high power electric energy is available. That is used for ionizing the gas. Here the gases we use something like noble gases like xenon or argon or krypton. These gases will be ionized by putting a high potential across the anode and the cathode. And these ionized gases are attracted towards the nozzle by means of the cathode, where the electrons are there which will attract the positive ions at a very high speed and ejected out through the nozzle, giving a very high ISP, something like 3,000 to 4,000 seconds. In the electromagnetic, again, a magnetic energy as well as the electric fields are created to ionize and then to make it plasma and then eject the matter through the nozzle. So these are all the various principles which are used for electrothermal or electrostatic and electromagnetic. One point to be noted is that electrothermal, you may get a slightly higher thrust, but then ISP compared to electrostatic is low. Electrostatic, you get a very high ISP, but the problem is you get a low thrust because the ions are getting ejected. It will be in millinewton. Electromagnetic is also of the same kind. You get a higher ISP or higher efficiency, but the thrust level will be on the low. So all these things forms part of future or even current satellite propulsion. People are already using. US has already used, Europeans have used, and we are also planning to use electrostatic propulsion in our upcoming satellite called the Technology Development Satellite, which we are going to fly in the next mission of PSLV in the first half of this year. This static propulsion also we are using it. And this is only the basic, the building blocks. For electric propulsion, you need three important things. One, you need the power control. That is called the power system, which will have the required electrical power. And then there has to be an electronic control system. Second thing is a feed system. You need a gas. It should be stored in a bottle and that to be admitted to the thruster by providing certain regulators and wires. So that is called the feed system. And the third one, of course, the thruster, where the electric thrusters are needed, where it consists of anode and cathode, where it is getting ionized and then it is pushed out through the nozzle. So this is the building block of the electric propulsion system. And electrothermal, already we have seen, we are putting coils around the chamber to heat the propellant and push it through the nozzle. It's a simple thing. Vasimir, that is a variable specific impulse magnetoplasma thruster. It is again a form of electrothermal. It is also a form of electromagnetic RF kind of a thing. Basically, the RF is used. Radio frequency is used for heating the propellant. By varying the radio frequency, the heat energy can be varied, the thrust can be varied. That is why it's called variable specific impulse. ISP can be varied. So it is again a form of electrothermal. And moving further, we see the electrostatic. Here again, as I already mentioned, you have an all-effect thruster, which creates a magnetic field to trap the electrons once the gases are ionized. And then these ionized gases are attracted towards the cathode by means of an electric potential between the anode and cathode. And very high velocities it attracted, and that gets ejected through the nozzle at even 10,000 meters per second, creating very high ISP. So this gives a very high ISP but low thrust. Moving further, this we can see the xenon, argon. It is only the graph showing what is the kind of ionization potential that is needed to ionize the gases. You can see the xenon, which is shown in a yellow, the dotted circle. That gives the least ionization potential. Whereas krypton and argon, they are all noble gases. It requires slightly more ionization potential. So generally we use xenon, but then xenon is costlier. We can also use argon, but argon has got a higher potential. So it can be used either way. It all depends upon what is the cost that is, you can put it like that. And now electromagnetic, I think this we have already explained. It is a magnetic field is created to trap the electrons, and then you have a high electric potential acting between anode and cathode to attract the ions, and then that is how the propulsion also you are getting. So the final thing is basically the propellant-less propulsion. This is a very interesting thing called a solar sail. Once the satellite is injected, doesn't require any propellants at all. It will simply, a big surface area will be there. Even it can be as high as 1,500 meters square, a 50 meter by 30 meter kind of a sail, a thin membrane, as shown in the picture on the right side. You can see a thin membrane will be there, and that will be pushed by means of a solar pressure or the photons that will be acting upon it. By changing the momentum, it creates the force, and that force pushes the satellite also forward. So this is a kind of propulsion device which does not require any propellants, but then it is available free in space using the solar pressures. But then this we can use it only within the solar system, but beyond the certain planets, the solar power source will be less. So for deep space or interstellar space or beyond the solar system, this may not be viable, but within the solar system for interplanetary mission, these kinds of solar sail is always, advantageous, which is already, like a mission called IIRS, that is interplanetary kite. It's accelerated by the radiation of the sun. So using the radiation of the sun, acceleration is got, and like a kite, it will be flying between the planets. So IIRS mission has successfully flown. Similarly, they have the night sails. 2 missions were there in 2015 and 19 of Planetary Society of US. They are also there. So this is a very feasible option, which is called a propellant-less propulsion. Something like a sailboat, what you do in a water, like wind pressures it blows, something like that. So I think with this, I conclude. And thank you very much. I think in a short time, we have gone through the chemical propulsion. We have seen the various propulsion, solid, liquid, bipropellant, various kinds of cycles. Also, we have seen the advanced propulsion, including the thermal, electrostatic, electrodynamic, magnetic, as well as the nuclear, thermal, nuclear, electric, and also the propellant-less propulsion and so on. So I think with this, I conclude. Thank you very much. Now, over to the audience for any questions, please.
Yes, sir. Now we will see the questions are there, so we'll wait for that.
Few questions are already there in the chat box.
Maybe you can see the chat box. Chat box, I think we are not seeing anything as of now.
Please click the chat box.
We have clicked the chat box actually.
Okay. Maybe I can see some questions.
Okay.
Right, sir.
Yeah. Shall I?
Yeah, please go ahead, sir.
Yeah. The first question is what propulsion technologies could enable interstellar missions within the next century? How might propulsion systems evolve to enable autonomous exploration of distant exoplanets?
Yeah, this is what we just explained. For the interstellar or interplanetary, or even to explore the exoplanets, we need a deep space propulsion system. So where we can think of the nuclear propulsion, this is one very promising thing, because you can store the nuclear fuel and then it creates a very high efficiency. So you can reach the distances in a very short time when we are talking about that. And even it doesn't require even a electrical power, or from the solar power it doesn't require, because the fuel is stored on board, and there you can generate the heat energy. Heat energy can be converted to electrical energy that can be used for powering all your satellites. At the same time, that heat energy can be used for converting your liquid propellant to gaseous propellant and to exiting the nozzle. So nuclear propulsion is one promising thing, that is for the solar system to another solar system or interstellar space, if you want to explore the universe and things like that. Otherwise, within the solar system means, the satellite electric propulsion. It is called electrostatic, or it is called the stationary plasma thruster, like a Hall effect thruster. This is again, that I already explained, using an electrical power, you need to ionize the gas. Already the noble gases, which has got electrons in the outer shell as octet, you need to knock off an electron so that it becomes positively charged ions. And these ions are accelerated, creating a very high ISP, but with a very low thrust. But this is again, the satellite called SMART, used by the Europe. They have used it even for travel to moon also. So the same propulsion can be employed to travel to Jupiter or to Mars or any other planets. Only thing, it takes a very long time because it is very low thrust. Otherwise, if you want to go fast, and you can use nuclear propulsion also. Over.
Okay.
which has come in the chat box. He's asking what is Vasimir engine?
Wow, Vasimir was VASIMR. Basically, it is a variable specific impulse, magnetoplasma thrusters. That is called the Vasimir engine. Actually, this Vasimir engine uses the principles of RF energy, radio frequency. You use different radio frequencies in a very high, megawatt to ionize a gas. So by to heat the gas. Once you heat the gas, this gas becomes thermal energy increases, pressure will increase. This high pressure gas will be exiting through the nozzle. And this you can. Why it is called variable is because depending upon the RF frequency, you can vary the kind of the pressure as well as the flow rates, so that your thrust generator for a given flow rate will be varying. That is why the ISP it varies. ISP is basically because thrust over a unit mass flow rate. So this you can vary by varying the RF frequencies. So it is something like a electrothermal. Means you are heating the gas and then you are pushing it through the nozzle. So here it is a Vasimir, means variable specific impulse. So here the heat is obtained by the RF energy. RF generators will be there to generate very high frequencies, and that will heat the propellant, make it into plasma, and then push it through the nozzle at a high pressure. You get a good thrust also. That's why that is called the Vasimir engine. Yeah.
Any more questions? Basically, in the chat box, I'm not seeing any further questions. So, from your end, if anything has come, please let us know.
Yeah. One question is there. What are the challenges in using cryogenic propellants compared to HTPB-based solid propellants, as in theory, cryogenic propellants are giving better ISP and thrust?
Yes, sir. This also we have just described, that the difference between solid and cryogen. As you know, always cryogen is preferred because even a small fuel is sufficient to get a good amount of thrust. It has got a very high energy potential. It is because of the characteristics of the cryogenic propellant. We talk about liquid hydrogen. It has got a huge heat capacity. So as asked, this HTPB, basically it is a hydroxyl terminated polybutadiene. It is basically a binder which is used in a solid propulsion. And in a solid propulsion, the fuel will be aluminum fuel, and there will be an oxidizer called ammonium perchlorate. These two are joined by the HTPB binder. The ISP, or the specific impulse of these kinds of solid propellant, is in the order of 300 seconds. Whereas when you talk about the cryogenics, where you use the liquid hydrogen, liquid oxygen, the ISP, or the specific impulse, is almost 1.5 times of that, something like 450 seconds. So for a given quantity of propellants, you can get a maximum thrust impulse. But where you use these kinds of propulsion is very important. I need a solid propulsion device for a bottom or for a core stage, booster stage, because you need a huge thrust, and then in a very short time, which always my solid propulsion system will give me. So there will be a compromise on the performance, but then you need a higher thrust because you need to overcome the gravity of the air when you are taking off from the air. Whereas if you want to use the same cryogen for the booster stage, of course, huge quantities of cryogenic propellant have to be stored. And since the liquid hydrogen and all, the densities of the order of 70 kilogram per meter cube, compared to, even for a liquid, it is something like 1000 kilogram per meter cube. Now the cryogen is 70 kilogram per meter cube. You need a huge volume of the tank. So the tank size will go up, the rocket size will go up. So finally the aerodynamic load will go up, and you find that the mass of the total system will go up. So it may not be advantageous for you to use a cryogenic propulsion system for the booster stage compared to a solid. So each has got its own merit and demerit. Even in some launch vehicle like Ariane 5, which the Europeans have used, they are having two solid boosters, P230. You might have seen that configuration. But then they are having a core, even the cryogenic engine is also there. So it is a combination of solid and liquid. Solid has got its own advantage, where you get a huge thrust in a short time, whereas liquid hydrogen and oxygen, it has got a higher ISP. But then for getting a huge thrust, you need a huge flow rate, huge quantity to be stored. So that dictates, the parameter that is dictating is the size of the propulsion system or the tankages. That again, the size of the launcher will go, aerodynamic loads. So it is a trade-off. You need to do all these trade-off study and then arrive at what is a feasible solution. Otherwise, both systems can be used, but most of the systems, either they use a semi-cryogen at the booster or as a solid or a storable. But cryogen also certain cases used, but then these trade-off studies must be done. Over.
Okay, maybe a last question. What propulsion systems are best suited for asteroid mining or establishing infrastructure on the moon or Mars?
Yeah. So this again for asteroid mining, something like even a solar sail is one thing, which always if you are talking about, our asteroid belt is there, which is between the planets. So always you get a solar thing. I think some systems they have used for asteroid called Vesta, some like this, some advanced propulsion systems have been employed. Either you can use a nuclear propulsion or even electrostatic, that we call it as a Hall effect thruster propulsion, which is actually a electrostatic propulsion. This also can be employed. Only thing, it takes a long period of time to reach the asteroid. So these are because with a less amount of fuel, you can reach the target with a but in a long period of time. So even for asteroid mining and all, we can always use, even for going to Mars or Moon also, this electrostatic propulsion can be employed. But then if you want a faster travel, of course, our Chandrayaan mission as well as Mangalyaan mission, we have used our extra-orbital propulsion, like something like MMH and MON3, monomethyl hydrogen and nitrogen tetroxide, because that the distance could be covered in a matter of few days and few months. For example, extra-orbital system when we use in Mangalyaan, we took almost 300 days to go from the Earth's orbit to the Mars orbit. So, the Mars is a neighbor orbit. Even to reach there, you took almost 1 year or something like 300 days. If I use the static propulsion or the electrostatic propulsion, where the thrust is minuscule, something like in millinewton, you will take years to weather. So it all depends upon what is the kind of exploration that you want to do, whether it is immediate or you can allow for a long period of time. If that is so, long periods are allowable means you can always use electrostatic propulsion. If it is a shorter period you want to use, you can go for even the chemical bipropulsion, something like what we use for Chandrayaan and Mangalyaan. Over.
Okay. With this, we can stop this session. Thank you very much, Hutton sir, for providing an insightful and informative lecture, and also a very simple manner. You have explained all the questions as a teacher. Thank you once again.
Thank you very much.
Yeah,
thank you.
And thanks to Mr. Nihal also for moderating this session. Thank you once again for supporting our START program.
Thank you, sir, Praveen sir, for giving this opportunity. I thank Mr. Nihal also and my staff here and all the audience, students. Wish you all the best. Thank you very much.
Thank you. So you are a Now we are going to hear the next and 19th lecture of this series, and the topic of the lecture is Docking in Space Technologies, Challenges and Possibilities by Dr. Koteshwar Rao from UR Rao Satellite Center, ISRO, Bangalore. We have with us Mr. Siddharth Arora to moderate this session. I would like to introduce the moderator. Mr. Siddharth Arora completed his Bachelor's of Technology in Avionics from Indian Institute of Space Science and Technology, Trivandrum. He joined Indian Space Research Organization in 2023 as a member of Chandrayaan-4 study team in Science and Space Exploration Program Office at URSC, Bangalore. He is currently working as project manager for Chandrayaan-4 and SpaceX-2. So I am passing over to Mr. Siddharth to moderate this session.
Thank you, sir. Good evening, everyone. Today, we have the privilege of hosting a distinguished expert in the field of space technology, Dr. C. Koteshwar Rao. I have had the honor of working with him, and I can confidently say that he's not only an exceptional professional, but also one of the finest individuals I've had the privilege to work with. His expertise, passion, and leadership style make him an outstanding asset to the space community. Dr. C. Koteshwar Rao is a scientist engineer, SG, at the UR Rao Satellite Center since 2005. He served as Deputy Project Director, Spatial Test of Chandrayaan 3 and Head Mechanical Design and Measurement Division of System Integration Group. At present, he is working as Project Director, SpaceX 2 and Associate Project Director for Chandrayaan 4 mission with Science and Space Exploration Program Office. He did his PhD in Mechanical Engineering at Indian Institute of Science, Bangalore in 2018. He has 28 years of teaching, industrial, and R&D experience. He has authored 4 journals, 52 conference publications, and has 2 patents. He has been awarded as Young Scientist by Society of Aerospace Manufacturing Engineers in the year 2009 and Young Scientist by ISRO in the year 2012 for the development of photogrammetry application for spacecraft alignment activities. Please join me in welcoming Dr. C. Koteshwar Rao, who will be delivering a lecture on docking in space, technologies, challenges, and possibilities.
Thank you, Siddharth, and thank you, Praveen, sir. It is an honor to deliver this lecture here. I welcome all the audience. And my lecture is Docking in Space Technologies, Challenges, and Possibilities. So let us see what we have there for you. Go to the next slide. So I will be talking about docking and berthing of spacecraft, and then what is the need for docking in space and brief history and technologies associated with docking in space. And then we'll spend some time on mission phases and constraints to be addressed. And what is the specification for low impact docking mechanism? And what are the ground tests to be done to prove before launching any docking mission? And what are future opportunities and research area? And then we'll conclude. Go to the next. So let us try to connect with this topic with our day-to-day life, what we observe. Okay, so left side I have given you 2 racing cars, and what I have googled is some 500 km/h is the maximum speed one racing car can run. So if 2 cars are there and they want to chase each other and they want to just feather touch one car, want to touch the other car, and that has to be a feather touch and should not be colliding. So what has to be done? So one is when both the cars are driven by 2 drivers. So the driver should know what is his speed as well as what is the speed of the next spacecraft, right? So then he has to see how far that is and how much, and it all depends on his judgment. If judgment goes wrong, then it will be a collision, and that collision will be an accident basically, right? So the complication further increases if you remove the driver and you call that as an automated car, where driverless car should be there. So then again, both cars have to interact with each other and they should know their relative speed and they should know where they are, how to navigate and without collision, and a safe touch, how can be performed. Okay, so this is the complication on ground. We can visualize automated vehicle also we have read. But what happens, the complication further becomes multifolds when we go to the space. So space, here our speed will be 50 times more, around 27,000 km/h. And at that speed, 2 different space vehicles are traveling and they have to come nearer to each other and then dock. Okay, so this is how this gives you a flavor like what is required to be done to bring them closer and join them. So can we go to the next slide? So here automated car again will revisit. If we want a driverless car to do all these operations, he needs GPS for tracking where he is and how to navigate, and some LiDAR can be a sensor which can scan the complete area and find out where he is, what is the total environment, and without any collision, if you want to dock with another vehicle or touch another vehicle, what has to be done, how he will either he will reduce the speed or increase the speed or which direction he should go. And again, when there is no driver, then some eye should be there. That eye can be a camera. And AI, artificial intelligence, can be there, so that it has to be programmed in such a way that taking all these input from different sensor, it should be able to go in a proper direction and do the required operation. And then there are different sensors called radar and ultrasonic. So this is how the automated or driverless car can be designed. Now we will go to the next. So to connect this to space vehicle, I have given you, like, now you can connect, okay, how driverless car can be operated and what are the sensors required. Now if we want to dock or berthing of the spacecraft, first let me introduce you with the terminology what we use in this technology. One is called docking, another one is called berthing. So both are terms used for joining two space vehicles in space or two spacecraft in space. And this connection can be temporary or primary, partially permanent, and like our space station modules. So docking term is used when two separate free flying space vehicles are joined together automatedly. They are freely flying. Okay. So and they have to come closer to each other and dock very softly so that they are not colliding with each other. And the second term, berthing, is used. There are two different vehicles or spacecrafts. They are in space and they are very far from each other. First, you bring them closer, such that suppose one spacecraft is having a robotic arm, and the moment the second spacecraft comes nearer to it, it will be able to capture that spacecraft and then bring closer using that robotic arm and then join it. So that second operation using a robotic assisted docking is called as berthing. So these are the two common technology or terminology we use in docking. Go to the next, sir. So can we go to the previous slide? And so here, right side, you can see two spacecrafts are docking on the top side. So where they are freely flying inside one to the next. And second, berthing, where we have shown one robotic arm, which is capturing a vehicle or spacecraft and bringing closer to it. Go to the next. So here, why this docking is required, the need for docking in space, right? So if we see whatever spacecraft we can design in ground, that mass of that spacecraft is limited with the launch vehicle capacity. So generally, launch vehicle can launch from, like, say 2 ton or 2000 kg to say 6000 kg or beyond also. Different countries have different range of launch capacities. So within that launch capacity, you have to design a spacecraft. Now, a spacecraft has to carry some fuel also. That fuel is a main load carrying element in a spacecraft, which will decide the life of a spacecraft. Suppose a 4-ton spacecraft you design, then in that 2000 kg of fuel you are going to fill. And when it goes to the orbit, that 2000 kg fuel will be sufficient for, say, 10 years of life. After 10 years of life, that fuel will be exhausted. But all elements of the spacecraft are in a good condition. You want to say that, suppose there are two options. One is you deorbit it and bury it so that, like, its life is over. But you want to enhance its life, then you have to supply that fuel to that spacecraft. So that term is called refueling. Like our vehicle, no, we go to the petrol station and we can fuel our car. But here we cannot go to a petrol bunk. Instead of that, petrol bunk can go to the spacecraft. So that is called refueling, where we will fill propellant in a spacecraft and send to the orbit near the spacecraft where fuel is not there. And these two spacecraft can dock each other and supply this fuel to the other spacecraft, so that you are enhancing the life of a spacecraft. And resupply, like space station, you have seen that Sunita Williams was there, and she has to there for more than a year. So if she has to there, then suppose she exhausts all her eating or whatever cargo requirement is there, to survive there. So after that once she exhausts all her ration, so you have to send that ration, eat food or clothes from Earth to that space station, right? So that is called resupply. So for that also cargo missions are there, which can fly from Earth to space station, dock, and then supply this material to that, undock and come back. Then it also allows module to module connection. Like a space station cannot be built with a single launch. So multiple modules may be there. Like as I told, once launch capacity is suppose 4 to 6 ton. So you design a module of that 6 ton capacity and launch in a rocket, launch vehicle, and it goes and stays in some orbit. Okay. After that, there are multiple modules to be connected to this module, so that a bigger module can be generated in space. So that module to module connection can be done using docking technology. Then comes facilitates satellite servicing and maintenance. As I told, refueling is one of the servicing or maintenance. Another can be, suppose some part is gone bad, then this spacecraft can be sent from here, which can dock and provide that relevant equipment to that, so that the life of the spacecraft can be enhanced. And then finally, this comes as a space exploration and development. You know that you want to go to the moon or Mars or any other planet. The distance is very, very far. You cannot carry the complete fuel with you. So you go halfway and dock with another, say, petrol bunk, where you can carry the required fuel to go to the next. So, or you land on moon first. From there, again, when you want to go to the another planet, there itself you have sufficient fuel. From there, you carry the fuel and go to the next. So, like docking is very important in addressing all these challenges. Sir, can you go to the next? So coming to history is very important. Like we should know from where our journey started. When was the first docking attempt was done? So first attempt was done by NASA in 1966, where Gemini 8, that was, and their crew was Neil Armstrong and David Scott. So these two people were a crew, and they one more vehicle was their Agena target vehicle. So that Agena target vehicle, they docked with Agena target vehicle. So it was a crew docking. Okay, so where a crew is operating the vehicle and controlling and then docking to. So this was the first attempt where they have proven this docking technology. After that, USSR, like Soviet Union has done one experiment where without crew, automated docking they wanted to test and demonstrate. So their Cosmos 186 was docked with Cosmos 188 in 1967. So that was the first uncrewed or automated docking experiment was demonstrated. So that was the 60s era. Then 70s era came, where two different nations, like one from NASA and another from Russia, they wanted to dock with each other. That is Apollo and Soyuz spacecraft. So that successful docking was carried out in 1970s. And 80s was the era when this development of space station started. And space station, as I told, it cannot be built with a single launch. It has to be multiple launch, multiple modules. All modules should have a docking capabilities. So that started. And then 1919 onwards, this international cooperation of space docking started, where they started looking for how to standardize when the space station is there in place. So how other countries can come and dock. So there the standardization started, and you know that China also is one of the country where 2011 they have demonstrated their docking technology, and now we also are in that list. India also has demonstrated its docking capability. With that, we have become fourth country to demonstrate this indigenous docking technology. Sir, can we go to the next? So these are the terminologies used in docking. Like one is a Russian docking system is called a probe and drogue, where one conical shape of docking attachment will be there and other probe kind of thing. So both will come and dock to each other. and international docking system standard. So NASA has standardized its interfaces for docking, so that they have named it as International Docking System Standard. So this literature is available in net, so anybody can refer and design their docking system and go and dock with ISS. There are protocols involved. All those protocols, whatever requirements and safety standards, everything is documented in that docking standard. Then, as I told, crewed and uncrewed docking. So, NASA Gemini was a crewed docking, and Russian Cosmos was uncrewed docking. Then cooperative and non-cooperative docking. So one spacecraft is already there in space, and that has that spacecraft. So that spacecraft means it has required features on it which can be seen by another spacecraft. So feature means there can be a target, so or some light bulbs are there. So you should know which direction you have to move, how to align to the spacecraft. For aligning, you use different kinds of target. Okay, so that target, if they are present in the spacecraft of say the target which is waiting for another spacecraft to come and approach it, that is called target spacecraft. The spacecraft which goes near to that target spacecraft is called chaser spacecraft or active spacecraft. So active spacecraft will have a lot of sensors. That sensor should be able to recognize the target available on the target spacecraft. So that is called cooperative docking. If this kind of features are available in both the spacecraft, so that both can communicate with each other, that is called cooperative docking. And non-cooperative docking, you don't know anything about the spacecraft. You go near to the spacecraft and inspect it, and then see which features you can use for docking and how to docking. There itself you form the strategy. So that comes under non-cooperative docking. Then there is a term called V-bar approach and R-bar approach, where the motion is parallel to the target's orbital velocity. So that is called, so there will be orbit in which spacecraft is orbiting, and in the same orbit, the motion of another chaser spacecraft is parallel to the target orbit velocity. Then it will be called V-bar approach. And R-bar approach, motion should be orthogonal or perpendicular to the target's orbital velocity. So these are the terms which we use in docking. Can we go to the next? So this is few diagram like Russian docking system, as I told, cone and drogue type, or probe and drogue type. So here there will be a conical feature. Inside that conical feature, one probe should come and dock. So it will enter into that so that it can dock. And next comes androgynous peripheral attachment system. So unlike there, one like probe we can call as a male feature, and another is a female. So here these two are joining. So this is one. So always you cannot interchange the feature. So here what happens, androgynous, in that anyone can become a role reversal is possible. So that way any feature can be supported by this. It can be like either a male feature or a female feature. Anything can come, and androgynous peripheral attachment system can support that. So can we go to the next? So another way is you go and grab it. Okay, so that is called a claw type of docking mechanism, where one already lever is available or a bar is available, and you can see the left side, top left corner, you are able to see that there is claw is available. So this claw will go and grab this lever. So with that, docking can happen. And common berthing mechanism, again, is a standard where defined features are available on both sides. So using this, they can dock to each other. Then comes low impact docking system. So here also, like Stewart platform, they have built initially to prove that whenever they are docking, there should not be any impact or collision. So that way, this initially whatever extended area is there, that will absorb all the initial shock. Then once that grabs, then the further it will come and touch to the bottom of the ring, and where it will rigidize to each other. And then NASA has standardized this with a Stewart platform, which they have initially called as a NASA docking system. and later they have defined as IDSS. So there, for initially soft capture, there will be a steward platform, blue color ring you are able to see. So that will first receive the chaser spacecraft, and then once it receives, and here first level of docking happens, that is soft docking, then it will all the legs of steward platform will retract, and then this blue color ring will bring the spacecraft closer to the next ring, where both will come very closer to each other, and then the rigidization happens. So these are the different mechanisms what is being used. Can we go to the next? Now, as I told, automated vehicle needs a lot of sensors for docking. So here also there are different technologies which are required in space. So first and foremost is sensors and navigation system. So here left hand side I have shown you one vacuum cleaner. Okay, nowadays automated vacuum cleaners are available. After work is completed, it will go and dock to its charging station automatically. Okay, so for that it should have a different sensor. So similarly, and it should be able to navigate itself automatically. So that the similar technology like sensors and navigation system should be available on our spacecraft also. So here RF sensors, radio frequency based sensors, and radars, GPS receivers, visible and IR based or EM based sensors are required, or lidars are required. And also on the target side, we should have some targets which these sensors should be able to recognize, or some corner cube reflectors should be available. Suppose you are throwing some light on that target spacecraft, then active spacecraft should receive that light back. With that, it will be able to align it with the docking for docking. So now top right side, I'm showing the docking mechanisms. What are the docking mechanisms adapters? Already we discussed this in the previous slide. So here you can see yellow color ring is on the top side, which is a passive ring, and blue color ring is having some active ring, where some extended portion, between these two, yellow and blue, one ring is shown. So that is having some petals. So that is standing on some legs which are called steward platform. So these two will be in this condition before docking, and once this yellow color ring will come to the intermediate ring, it will grab it and then bring closer to the blue color ring, so that blue color and yellow color both will merge with each other, and then rigidization happens, and this joint will be a permanent joint then onwards, partial permanent, or it can be a permanent. Then to do all these operations, like you have to navigate, you have to move the spacecraft. So both the spacecraft, as I told, they are moving with a very high velocity, but relative velocity of these two, relative position of these two should be known. That will be sensed by the sensor, and then once the sensor senses that, then some propulsion system is required and control algorithm is required, so that you can push one of the spacecraft, either you reduce the speed or increase the speed, so that it goes closer to the spacecraft, and then further docking operation happens. And all these things can be possible because spacecraft is orbiting, say, from here 500 kilometer above Earth, and that satellite you have to communicate from ground. Then you should have required communication system and data exchange protocols with you. So these are the minimum required technologies which are essential for docking in space. Sir, can we go to the next? So here mission phases, if we look at, then first you have to do a launch. Okay, so here all steps I have given like a ladder. So first blue color, it starts with a launch, where injection into a desired orbit you do. And once you have launched there, then they will and spacecraft is injected by the launch vehicle. Then the launch satellite will start drifting. Okay, initially it will have some injection velocity, and you have to arrest that injection velocity, and then reduce the separation velocity and bring them to a desired position. Okay, so say you have both the spacecraft are moving apart, and their inter satellite distance is building up. First you have to arrest that and bring them to a desired, say initially their inter-satellite distance is 200 kilometer. First you arrest that and bring them closer to 20 kilometer. Okay, and from there this rendezvous starts, and rendezvous based on first a relative sensor, and then you do docking. And once you do the docking, the composite, both the spacecraft are together, are called as a composite. That composite you have to control. And if there is a provision after docking, if you want to do power transfer, that also you carry out, and then undocking, and then payload operations you do. So this is a total life cycle from launch to payload operation. And if you see on the bottom side, I have given you a timeline where this 5 kilometer is a starting point, where you the inter-satellite distance is 5 kilometer. Two satellite, one is on the left side there is an active spacecraft, on the right side there is a passive spacecraft. On the bottom of the screen you can see this, and bottom side I have given some bullet, like 5 kilometer we call that as a inter-satellite distance. When it is 5 kilometer we call that as a far rendezvous phase. Okay, so here you have to first find out what is the relative velocity, what is its relative position, and you hold them. You try to control this 5 kilometer, and with that inter-satellite distance of 5 kilometer, they will be orbiting. Okay, so you lock their position, and from there you start moving towards this passive spacecraft. Active spacecraft is moving towards passive spacecraft. From 5 kilometer you come to 1.5 kilometer. So up to this you are like using GPS or RODP, that is called relative orbital parameter determination. So with that you are able to push the spacecraft to 1.5 kilometer. And from that 1.5 kilometer again you come to 225 meter, and with all these whole point you are continuously calibrating all your sensors which are required for doing this docking operation, and they are telling you the actual health parameters of the spacecraft, their relative velocity, their relative position. All these things are told by these sensors. So you calibrate them well, and you ensure that you have a proper hold of these two spacecraft. Then you come closer to that 225 meter, and there our near rendezvous phase starts. Their near rendezvous phase, 225 meter is a good distance from where I can start using optical sensors. In optical sensors, what happens is it has the line of sight should be aligned to the active to passive spacecraft. The line of sight should be aligned. So that starts coming within the visible range. So that is that's why we call that as a near range phase, near rendezvous phase. And from there we go to close range rendezvous phase, that is 100 meter. From here onwards, all optical sensors one by one they come into acting, and then up to 15 meter we go. There again we hold, and we ensure that all our optical sensors are in loop with the control guidance, and they are giving us the proper whatever desired accuracy or not. Then we go to 3 meter, and from there we go closer to the spacecraft, and the final approach one, and final where the soft docking will happen, and final approach to the final rigidization will happen. So these all are the phases where every step is very, very important, and it will be done very meticulously, and because safety of the spacecraft plays a very, very important role. So can we go to the next? So here, when you are designing a docking mission, so as I told, different sensors are used, and then spacecraft has to be designed. So what you have to look at is you are in space, you are not alone. Sun also is there, sun, moon, everyone, different types of stars, everything is available. So that means some source of light is available. So whenever source of light is available, there will be a chance that that light can enter into your sensors which you are going to use. Like whenever you want to capture a camera photo, so you should not click in the direction of sun. You have to click the camera on the if the sun is behind you. Okay, so similar concept is applicable here also. So all your sensors which are present on the docking spacecraft, either it can be active or a passive, so their sensor should not see the sun when they are operating. If they are seeing a sun, what will happen is that light will enter into this sensor, and it will try to saturate its performance. So, but you cannot make your sun geometry, sun to your spacecraft geometry always constant, because always your spacecraft position is changing, sun position with respect to Earth is changing, all your this complete geometry is varying with respect to time. So if, the left side, left top corner, we have shown one orbit and one sun, and this position is not constant with respect to time, and it is a function of time, right? And all the parameters you should have a control when you are operating for docking operation. Next, bottom of left side, I have given you sun aspect angle and number of days. So every day, every moment, the sun aspect is changing, and that goes from 0 degree to 68 degree. And that time your solar panel satellite should have a power, and that power comes from the solar panel, and solar panel can generate more power if the sun aspect angle is perpendicular to the solar panel. If it is not, then what will happen is you will sunlight cannot be generated. So that's why the sun aspect angle from sensor point of view and power generation point of view plays a very important role. So not only this, you have to communicate with the spacecraft. So your ground stations, and you can see there on the right side of the top side, there the orbit is shown, and the trace of that orbit or the satellite path on the ground is shown with a yellow curve. Okay, so that is shown as a sinusoidal curve. So wherever it is passing below that trace, there should be a ground station. Minimum 1 or 2 ground stations should be there, so that they should be able to, whenever it passes through that ground station, it will be able to communicate. Whenever there is no ground station available, then it cannot communicate with the spacecraft. So that time you cannot know, you cannot command anything to the spacecraft. So what we do is, whenever there is a visibility, we upload all our commands in a sequential way, and that command will get executed with a timely manner. And then suppose even if it is not visible to us, those all commands will be operating. Suppose you have given a command to go from 1.5 kilometer to 15 meter, it will keep going, and in between you have given different operations, all those operations it will be doing. So at 15 meters, say you have again sighted that spacecraft with another ground station. From that ground station you operate, you download all the data and find out whether whatever commands you have given, those all commands are operated as per your requirement or not, and how is the health of the spacecraft, and next step, whether it is good to go. So these all things we have seen. So they are the constant when you are designing a spacecraft. And now comes your final approach when two spacecrafts are meeting each other. That time, what should be the approach parameters? So here you can see the displacement between two spacecraft along docking axis should be less than 0 to 10 mm, and perpendicular to docking it should be plus minus 35 mm, and angular misalignment should be from plus minus 0.5 degree, and their approach velocity, as I was telling, they are traveling with a velocity of 27,000 kilometer per hour, and from there you have to bring down to 5 mm per 5 mm to 15 mm per second between those two satellites. The relative velocity should be within this number. Then only it is safe to approach and dock. Okay, and perpendicular to docking axis, the velocity should be plus minus 1 mm per second, and rotation velocity should be plus minus 0.1 degree. So this much if you are able to achieve in orbit, then only it is safe for docking, and then our docking commands will be executed, and we go. And so to do this, this is a control flow diagram where there is a spacecraft, and there are relative absolute sensors that will tell what is the position and velocity, and then there are different blocks like PV estimator and orbital guidance and hold point control, and all these things are, there will be one closed loop guidance and another will be open loop guidance, and then relative motion dynamics will be computed from this, and then attitude estimator and attitude controller will decide, and this guidance hold point controller will decide how much delta V and torque to be provided to the spacecraft, and that goes as an input to thrusters, wheels, and torquers. so that will start controlling the spacecraft. So this is overall control diagram. Can we go to the next? So now you have designed the spacecraft, and before and you have designed a different algorithm and all sensors you have put, everything is ready. Before launch, you have to demonstrate whether everything is working as per your requirement or not. So for that, the way is test as you fly. So here the limitation is we have to test everything on gravity, and in space there is no gravity, and they should be there. They are freely flying on some orbit, and here that free flying you have to demonstrate. So if you see here, this is first test setup, which is called docking mechanism performance test. So here this is end-to-end docking verification from hold point onwards we do, and validation of autonomous rendezvous docking and undocking sequence we test. So for that, for free flying demonstration, we keep them on a air bearing so that there is no resistance from the floor and they are freely approaching each other. And here we demonstrate all the docking technology. Go to the next. Here in this case, this is called vertical docking experiment, and we want to characterize the docking mechanism and correlate the test result with docking dynamics with some simulation software. So here what we do is below part is the Stevet platform, and from top this docking mechanism is hanging so that this will come closer, and then you see whether all your parameters, and you try to adjust as per that approach parameters, and you see your docking is done as per your simulation. Go to the next. Here we test the complete sensor and NGC performance evaluation, which is called a rendezvous simulation lab. Here you are able to see 2 robotic arms, and those 2 robotic arms are kept on rail, which can on the rail it can move from 15 meter to 660 meter. So that guidance estimator, hold point control with flight docking sensor and onboard computer, everything can be simulated and their performance can be evaluated. Whatever I have shown in the control flow diagram. So all the parameters will be established and validated here before flying. So once all special tests are done, then the spacecraft will be launched and the docking operations are carried out. Go to the next, sir. So here future opportunities, you can keep clicking on this. So in orbit assembly and manufacturing, can you click on the screen? So here, as I told, you want to build a very large assembly and you want to try out manufacturing operations. So then this is docking gives an opportunity to us. Sir, keep clicking one more. And space power-based solar power energy, and then satellite servicing and maintenance, and deep space exploration. So click 2 more times. So this is how these all things are possible with docking technology. Can we go to the next? So these are the research areas. When you want to do this, like docking, you have to ensure that design optimization of docking mechanism of high precision alignment and capture. You can find out different ways doing that, and it has to be lightweight, compact docking system for small satellites. Then you can also do research on advanced sensor systems for precise navigation and docking. Every time you can come out with a further precise numbers of these sensors. And today is the era of machine learning and AI, so that also algorithms for docking and navigation and control. This is another area which you can try. And GPS denied navigation techniques. Suppose in near Earth, yes, GPS is available. When you go farther to a new planet or even moon orbit, there GPS is not available. In the absence of GPS, how you can navigate? Okay, so that technique also you can research. And then control system for smooth and stable docking maneuvers, and model predictive control strategies, robotic and autonomy, and material research for modular docking, easy assembly and reconfiguration. And space debris mitigation is another area where you first you go and dock with the debris and then you bring back, And docking strategy for planetary defense missions also is a new area which is coming up. So and also electromagnetic and tethered docking are few more keywords. So all these keywords can be used for research. And finally, to conclude, docking technology is an important domain of our future advanced space exploration missions, and research and development in these domains play a substantial range of capabilities. And SpaceX is a spacecraft launched by ISRO, India, and we have become the 4th country, and we have demonstrated successful docking of 2 spacecraft in orbit. So with that, I conclude, and can we go to the next? So these are few references and many more you can see with the keywords given in this slide. Can we go to the next? So this is a disclaimer. The contents of this lecture presentation are solely the views of the speaker and do not represent the official narrative of ISRO. With that, I conclude and thank all the participants for their kind attention. And now the forum is open for any questions. Thank you.
Okay, so we have questions here. So first one is it impossible to launch a whole space station in one go?
Yes. So this is yeah, definitely everyone should be able to visualize how big the space station should be, and more bigger. Then first you have to look at your launch vehicle capacity. And generally, if I take our ISRO launch vehicle capacity in the previous lecture, also it was mentioned. So suppose a launch vehicle capacity is 5 ton, and you want to make a space station very large, say 30 ton. So that means six times the launch vehicle capacity. That means you have to launch 6 times, and 6 different modules you'll launch with 6 different launch vehicles and go and dock them in space. So that way, in a single shot, you cannot launch a space station of that capacity. Suppose you are launch a space station, you are designing a very small space station of launch vehicle capacity, then you can launch in a single launch vehicle.
Okay, the next one is, how could space docking contribute to the development of a permanent lunar base?
Yeah, so space docking, like what you have to, as I earlier told, interplanetary missions need a huge fuel. Okay, and again the restriction of launch vehicle capacity, you have to have multiple launches. So what you do is first you define a base in between Earth and Moon, and there you keep launching and keep a station which you call as a fuel station. And when a space vehicle is going from here, it will go and first dock with that fuel station and carry the required fuel and go to the Moon. And while coming back also, it can dock with that fuel station and come back. So these are the few ideas with which we can, within the launch vehicle capacity, we can meet such kind of missions.
The next one is it possible to create our own docking system standards, and if any new design techniques can be proposed?
Yeah, so India has developed its own indigenized docking mechanism. And what happens is even NASA also, when they started, they also designed their own system. Every country has their own when they start. But when you start developing many more missions, so within your country itself, you need to standardize. If you don't standardize, you have launched 2 spacecraft, and there, if any mismatch comes between those 2 docking mechanisms, then you cannot dock. And when you collaborate with other international space stations or international space agencies, then their system and your system should match, and that matching can be done using standardization only.
Okay, so we'll take one more question. What happens to the space vehicle if docking method is failed in its path?
Can you repeat what happens to
the space vehicle if the docking method is failed in between its path?
Yeah, so failure, first you have to define what is failure means. So failure can be, first of all, as I told, the failure can start from sensing itself. You are not able to sense the relative position and velocity of the another vehicle, or failing can happen once you have come very closer to that, and when you give a command to go and dock, so that time you are not able to control the desired velocity, or you have achieved the desired velocity and they have joined together, but after joining, that mechanism is not supporting to move forward. Either any of the mechanism link is not working, and you are not able to rigidize and go further. So these all are failure criteria. If this happens, that means there is no further way forward. So you have to find out what is the solution to undo it, and how to undock it, and again try again one more attempt. So these are all techniques what we use in space.
Okay, so with that, we come to an end. I would like to thank Dr. Koteshwar Rao for so much information he has given to all of us. And I hope everyone has understood with all of his teaching experience. He has given us a lot of wonderful information at such a great pace. We could all understand. I hope it was helpful and your questions have been answered. So thank you all for joining.
And thank you. I thank Praveen sir and ISRO community for giving me this opportunity. I thank Siddharth for moderating this session. And I thank all the participants, all the students, and I wish them for their bright future. Thank you. Thanks a lot.
Thank you very much, Dr. Koteshwar, for providing a very informative lecture and well explaining the queries in a simple manner. Thanks to Mr. Sardar for well moderating this session also. And thanking once again for supporting the START program. With this, we are completing today's session, and we'll be joining back on tomorrow at 3:30 p.m. Goodbye, and meet you all in the same time tomorrow.
Thank you.